To a first approximation, the Earth's magnetic field can be thought of as due to a bar magnet located in the outer core of the Earth. As with many approximations, this leaves a lot of things out, such as the poles move as much as 60 kilometers a year. This doesn't count the daily wobble of about 40 kilometers. The poles reverse several times every million years. This rate is quite variable, with a couple of very long exceptions. The field strength across the Earth is also quite variable. The South Atlantic anomaly is a region where the field strength is roughly half that of the rest of the world. The total field strength has dropped by about 9% since 1840, when the first reasonably reliable measurements were made by Carl Friedrich Gauss. It has dropped as much as 50% since Roman times. There are a couple of the components to the magnetic field we're interested in at the moment: the total intensity, inclination or dip field, and the declination or difference between magnetic and true north. If you're navigating by compass, you care about the declination. The observed magnetic field is the sum of the main field produced by the outer core, which is about 95% of the field, fields generated in the crust and upper mantle, largely due to iron deposits, and disturbances produced in the upper atmosphere and magnetosphere. The equatorial ring current, which is mostly in the Van Allen radiation belts, is a source of the magnetosphere effects. This is the main field intensity. Units on this map are in nanotesla. A nanotesla may seem like an odd unit. That's a billionth of a Tesla. A Tesla is a fairly large unit. If you had a 1 Tesla magnet in your classroom, you'd have to worry about metal objects getting yanked across the room into it. The thing to note about this map is the rather wide range of field strengths across the world. The maximum is over near the magnetic South Pole at the moment at 66,000 nanotesla, and the minimum is in the South Atlantic anomaly at about 23,000 nanotesla. A nanotesla is the same as a unit called a gamma, which you will see in magnetic surveys for mineral exploration. There is another unit you will run into as a Gauss, that is 100,000 nanotesla, which is to say that the field strength averages about half a Gauss. This is the inclination or dip field. This is what you would expect if you had a dip meter. A dip meter is effectively a compass mounted with a horizontal axis. Most normal compasses, if you turn them on their side, they aren't going to work very well. But if you notice in the Atlanta area, you would be looking at a dip of about 64 degrees. Remember, this thing is pointing at something in the core mantle boundary. This is the declination field, and again, this is the one, if you're navigating with a compass, this is the one you care about. These lines change from year to year, and especially around the vicinity of the poles. A compass can tell you you're heading due north when in fact you are heading due south. This map shows the positions of the poles at 5 years intervals and the declinations. Something that is worth pointing out is going back to 1590 or thereabouts, a lot of the declinations are somewhat speculative. but otherwise they're not just totally off. You can watch where the poles are going and the fact that the declinations are doing really odd things. This is the field at about the time of the American Revolution. The Civil War. It may not be obvious from this map, but the north and south poles are not at the exact opposite point on the Earth's surface. In fact, the line between the two misses the center of the Earth by several hundred kilometers. Take good notes here. There will be a pop quiz after the video is over. What? Oh, sorry, never mind. The purpose for showing this page is to show what the spherical harmonics that are used to describe the magnetic field look like. The first term is not used because no one has found a magnetic monopole in the 50+ years they've been looking for them. The second row is the dipoles or the bar magnet effects. This would be the main term. North and a south, and then a north and a south in the equatorial plane. These are 4 poles, 6 poles, and so forth. There are several models for the magnetic field in use. The models use up to 195 terms, and these are updated every 5 years. No material is known that is a permanent magnet at the temperatures and pressures expected at the Earth's core. The core of the Earth is mostly nickel and iron. The outer core is known to be liquid because it does not allow shear waves to pass. The inner core is solid and does allow shear waves. Seismic waves are either compressional or P wave, which are like the sound in air or a shear. Shear waves are like twisting of the material they're passing through, and liquids don't twist. Liquid iron and nickel is a good conductor. A moving conductor in a magnetic field produces a current which can produce a magnetic field. Several research projects attempted to use the known geometry of the core to find an arrangement that would produce a self-sustaining magnetic field. After much computer time, an arrangement was found, and it had the added benefit of randomly producing a field reversal. The model concluded that the magnetic field is due to turbulent motion in the outer core. Motions that are entirely symmetric about the rotation axis will not produce a magnetic field. The fluid flows themselves are fairly slow. A given point may only move a few kilometers a year. The model also showed that what is happening in the core mantle boundary may look quite different at the surface. An odd requirement was that the inner core had to rotate faster than the crust and mantle. This was only 2 to 3 degrees per year in the model. A search for evidence in the inner core rotating faster than the mantle was started, and after a few years evidence was found that it does indeed rotate faster by roughly a degree a year, which is to say that every 359 years the inner core has rotated one more time than the crust has. The model also showed that a reversal will occur if the inner core's magnetic orientation is changed, and will fail if it does not. Some of the images they were showing, this one is showing turbulence with the north and south terms and mess in the middle. This is a few hundred years before a reversal. You notice there are north poles showing up near the south poles. This is during a reversal. There's more than one north pole, and for that matter, south pole. And then this is after the fact, and there's still little odd blips laying around in odd angles.